Now what happens when we have inductors in series? Consider the following scenario, where we have a voltage source V sub t that is providing a potential across inductors in series, where we have inductor L1 with a voltage potential V1, inductor L2 with a voltage potential V2, all the way up to inductor Ln with a voltage potential Vn. We recognize that elements in a series configuration carry the same current. Thus, if we construct a KVL loop around our system, we can sum our voltages. V of t would be equal to V1 plus V2 all the way up to Vn. Now, the voltage drop across an inductor is a function of the inductance and the time rate of change of current. That is, V of t would be equal to L1 di dt plus L2 di dt all the way up to Ln di dt. Since they all share the same current, they all share the same time rate of change of current. Thus, we'd have L1 plus L2 all the way up to Ln of di dt. And we'd say that LEQ is going to be the algebraic summation of our inductances of our inductors in series. Now, if we have inductors in a parallel configuration, we want to determine our equivalent inductance as well. Imagine we have a voltage source V of t that is applying some current to our system, where our current will enter our top node and split between our inductors. I1 will go through L1, I2 will go through L2, all the way up to IN going through Ln. Now, if we construct a KCL equation at our top node within our system, we'd have I of t would be equal to I1 plus I2 all the way up to IN. In terms of the individual inductances and voltages, I of t would be equal to 1 per L1, the integral of V dt, plus 1 per L2 times the integral of V dt, plus all the way up to 1 per Ln, the integral of V dt. Since these elements are in a parallel configuration, they share the same voltage potential across. Thus, our current running through our system could be expressed as 1 per LEQ, the integral of V dt. Thus, we can say our equivalent inductance can be expressed as follows. 1 per LEQ would be equal to the sum from I is equal to 1 to n of 1 per L sub I. We notice that inductors in parallel behave like resistors in parallel, and inductors in series behave like resistors in series. Now, let's use these concepts to determine the equivalent inductance of the following system. Say we have nodes A and B that is connected to a circuit, and we want to determine our equivalent inductance. To do such, we first recognize that our 3 and 4 millihenry inductors are in series. This would give us an equivalent inductance of 7 millihenries. Thus, we would have a 7 millihenry inductor in a parallel configuration with a 42 millihenry inductor. And that intermediate equivalent would be 7 millihenries times 42 millihenries over 7 plus 42 millihenries. Or we'd have a 6 millihenry inductor that would replace these three. Lastly, we would have a 3, a 6, and a 5 millihenry inductor in series. Thus, our total equivalent would be 14 millihenries.